Yeah, this is working. Okay, sorry for that. So my name is Van Olthuijsen. I'm a technical consultant for Filey Server. I'm also one of the workshop trainers. And today I'll be using the word we quite often. We did this, we did that. I already gave it away a little bit, but I'm doing a large part of this project together with my colleague, Leonard Post. So if there are any credits to share, then I need to share them with him. The learning objectives for today. First and foremost, V5M3 stands for VIPP5 Module 3. And we'll look at what the purpose is of VIPP5 Module 3, and we'll look at the matching use case, or actually we're going to be looking at two use cases, real-life use cases that Leonard and I are currently working on. We'll look at what a data flow could look like for VIPP5 Module 3, and we'll also look at the technologies that you can use to actually implement this data flow. The main takeaway for today, from my perspective, is the challenges that we ran into while implementing this data flow using these technologies and what action we took to overcome those. The presentation is split in 4 parts, so we'll start with the use case. What is VIPP5 Module 3? What does it look like? What's the real world problem that we're trying to solve? Then we'll look at how to transform data coming from source systems, which is not FHIR and in different forms, to FHIR. And we look at how to do that at scale, because it's going to be a lot of data that needs to be transformed. We'll look at how to accomplish data exchange once this information is in the FHIR server. As you'll see, there are 2 hospitals, they both have a FHIR server and they need to exchange this information with one another. And then once this information has been exchanged from one hospital to the other, we're going to look at how to process the incoming data. Now, VIPP5 is a Dutch acceleration program. It's a program with pretty well-defined requirements on what you need to meet. There's a deadline, and if you meet the requirements before the deadline, then you get funding. So it's a pretty good incentive we see here in the Netherlands for organizations, healthcare organizations, to start exposing their information as FHIR. There are 3 modules, and you can choose which modules you would like to implement. Module 1 is the exchange of BGZ and correspondence. Now, what is BGZ? BGZ stands for Basisgegevensset Zorg, and it's basically the Dutch version of the International Patient Summary. BGZ is composed of something called ZIPs, which are zorginformatiebouwstenen, and zorginformatiebouwstenen are the Dutch version of the healthcare information models. So you have a patient, you have a blood pressure measurement, you have consent, these types of information. So the BGZ is basically a collection of these ZIPs. And that's what you exchange with, in this case, the patient. And on top of that, you can also exchange correspondence. So for example, letters. The arrow goes in one direction. So it's the healthcare organization which is sharing the information with the patient using an app or a portal in a read-only fashion. There's also a module 2. That's where the arrow goes in 2 directions. So you're still sharing the information with the patient, but the patient can add some information to it. So you can fill in a questionnaire on how you're feeling today, or you can do a self-measurement like blood pressure, and you can write that information back to the hospital. You can also make minor adjustments to some of these BGZ informations, maybe your address or your phone number. Then there's module 3, and that's the topic of this tutorial, which is the same type of information that's going to be exchanged, but then it's being exchanged by 2 healthcare organizations. Now, the organizations that Leonard and I are working with are Maastricht UMC and Zuiderland. They're both situated in the southern part of the Netherlands, and we're, I think for MUMC, 6 months busy implementing now, and Zuiderland around 4 months, I think. The use case. There's something called a Prostaatkankercentrum Zuid. It's a center in the southern part of the Netherlands again, a participation of 5 hospitals, 2 of the ones I just mentioned. And what they do is they treat patients who have prostate cancer that has not spread. The reason that they concentrate this treatment is because of this quite intimidating device you see here on the right, which is called the Da Vinci surgery robot. It's very applicable for these kinds of treatments. It's very effective, but it's also very expensive and it requires training and upkeep of that training. So that's why these hospitals decided, let's take one center, there we treat these patients. So what happens is you're in one of these hospitals, you get diagnosed with prostate cancer, and then you get referred to this center. So that's the first flow of information coming from the hospital to the center. You get treated there, and then you go back to the original hospital for follow-up treatment, which is the second flow of information, so receiving of surgery outcome. Now, in order to transform data to FHIR at scale, we came up with a solution that involved, of course, the source systems. They have all of the information, something called an ETL pipeline that takes this information and transforms it to FHIR. And then at the end, we have the FHIR server where we store that information. And we'll go through all of these steps. So starting with the source systems, there's of course the EHR. In both cases, it's sub-Cerner, and in both cases, they are going to be replacing the EHR with a different EHR because sub-Cerner is no longer supporting the Netherlands. So the reason I mention that is because the solution you'll see later on is not integrated into the EHR, which would probably be the most logical solution. But since we're in limbo between these two EHRs, a different solution has been chosen. The EHRs produce zips, die zorginformatiebouwstenen. They don't produce it as FHIR, they produce it as JSON, but they have already standardized their output to some extent based on these healthcare information models. And as we'll see, that helped quite a bit. We have lab systems, medication, they output HL7 v2, and we have documents in PDF or PDF-A that all get fed into this ETL pipeline. Now, one of the first questions that arose very early on is how much data are we going to load into that FHIR server? Are we going to load everything? Are we going to load the last 2 months? Initially, we started with VIPP5 module 1. If you remember, that's the hospital and the PGO. And our notion was whenever someone logs in for the first time into this PGO, this patient becomes active. And then we really quickly need to get all of the information from the source systems and load it into the FHIR server. In order to support this concept of an active patient, we came up with something called a RAP, a registry of active patients. It's a nice acronym because it's the same in Dutch and in English. And what happens is that the first time you load a patient, so when a patient becomes active, you do this initial load. You reach out to all of the source systems, you get all of the data, you transform it, you load it into the FHIR server, and then you keep track of the fact that this patient has become active. So any subsequent updates in one of the source systems will inspect the RAP. Is this an active patient, yes or no? And if it's an active patient, it will feed the data to this ETL pipeline that then transforms it to FHIR. We're not doing module 1, we're doing module 3. So now a patient becomes active the moment he or she gets referred. And I always say he or she, but it's prostate cancer, so it's going to be a he. Two things that it does. First of all, it reduces the load on all of the systems. So there's an update, you check in the RAP, is the patient in there? No, okay, then I'm not going to do anything. So that's the first advantage. The second advantage is that it allows for an incremental increase in data. So if you have a cohort of patients that you need to treat, you just add them to the RAP, they will be initially loaded and from then on synchronized. So that's the source systems, all types of data that they are exposing only for active patients, and then they offer this information to the ETL pipeline. Now, ETL stands for extract, transform, and load. In our case, it's not really extract, it's more accepting the information because it gets pushed to the ETL pipeline. Then we take this information, we transform the data, and we validate the data. So those are two discrete steps. And then when the validation has been done and it's successful, we load the data into the FHIR server. You see these components here on the right-hand side, extract, transform, and load. Now, there are a bunch of variables in there, so the amount of data is going to be varying over time. It could be that there's a burst of incoming information, perhaps this cohort of patients that gets added. It could be that things happen in this pipeline, so it could be that a certain operation may take longer to process or that it might fail entirely. And when we started implementing this, we already knew that we needed to envision support for other functionality as well, so this needed to be flexible. So apart from just integrating these three discrete steps, we need something to, first of all, chain them together, and second of all, to make sure that they are orchestrated properly. What was a good solution for that, we thought then, and we know now, is messaging. So what is messaging? You see it here on the right-hand side. You have something called a message bus, and a message of a specific type gets placed on this message bus. And then there are consumers. And these consumers listen to messages of a specific type. So in this case, you have a message A, and you have a consumer of type A that picks up this message, does something with it, and then produces a new message, which could be message type B. It's very scalable. I won't go into too many technical details, but they're running in containers, and if you have Kubernetes underneath it, it means that if you have a certain flood of messages of a specific type, setting it up like this can spawn a lot of consumers that take these messages, process them, and then when the load decreases, you can scale down the number of consumers. So it's very scalable. It's also very flexible because there's nothing that ties consumer A with consumer B. They don't know anything about one another. So consumer A now produces message type B, but it could also decide at a certain point in time to produce a message type C. And then you introduce a new consumer that deals with that. So it's very flexible, and as we'll see, it's very easy to create different routes through this message bus. The last thing is that it's really robust. So out of the box, if we're looking at containers and Kubernetes, if one of these consumers fails, then the system itself will make sure that the new container gets spawned. But the message bus itself also has something called, for example, a dead letter queue. So if any of these messages are, for some reason, they fail or the component fails, someone gets notified on the fact, hey, we can't process this message. So you get a lot for free when you're using this message bus. There are two different implementations. One of the organizations is deploying this on the cloud using Azure, and the other organization is doing an on-premise deployment using Red Hat Enterprise Linux. And the rest of the talk is going to be focused mostly on the last one, the on-premise, because there we needed to do a bit more ourselves, and therefore we also learned a bit more. And this is the parallel to the orchestration thing that you just saw. So what does it look like? You have a new data message. So something gets pushed from the source systems to the ETL pipeline, and then a new data message arrives. The transformation component subscribes to that specific message. So it takes this new data, it processes it to fire, and then it produces another message indicating, hey, there is new fire data. That is the validation component who is interested in that, and so on and so forth. The second problem, which is actually related to choosing a messaging solution, is what type of messaging solution are you going to be using? So there are a few. You have RabbitMQ, you have Azure, you have Amazon. They're all tied to a specific platform, and they all require a specific implementation. Now, luckily, we were tipped by a colleague of the existence of a framework called mass transit. A mass transit is basically a wrapper around these three message buses. That gives you two main advantages. First of all, the implementation that we write as programmers is agnostic to the actual implementation here of the message bus. So we just tell mass transit, okay, create a new message, send this message. That's all we do. A mass transit will speak the relevant dialect, the relevant language of the underlying message bus. Which brings me to the second advantage. Choosing which message bus to use is just a matter of configuration. So you can just flick a switch and then you'll seamlessly switch from RabbitMQ to Azure to Amazon. So the customer is now running on-prem, but if they decide later on, okay, we want to move to the cloud, we want to move to Amazon, then they can just lift and shift this solution by just switching this configuration setting. The consumers, as I mentioned, it needs to be flexible. So the first route we had was new information adding up in the RESTful API, transformation, validation, and loading. But pretty soon we also needed to implement the deletion of data and the merging of patients. We'll go through all of them in a bit more detail. First of all, the RESTful API, which is the interface layer between the ETL process and all the other processes and the source systems. And this is what a RESTful API looks like, or at least what our RESTful API looks like. So they are divided in zips: living situation, nutrition advice, patient, consent, etc. What you do is you choose to, for example, post a new living situation, so add or update a living situation to the system. But we also support deleting of living situations on an instance level. And if you want to perform a patient merge, that's also just a call. So this is basically the switchboard that the source systems are using to choose what kind of functionality they want to trigger. The transformation component is implemented in C# using the Filey.net SDK. Now, why did we choose C#? We wanted to have maximum flexibility. So if it turns out during the project that we need to do more elaborate things, we know that we have a language at hand that can do pretty much anything. The Filey.net SDK has the advantage that it offers POCOs for all of the resources. So there's a patient in there, there's an observation in there, etc. And it also allows you to very easily shape them, add extensions to it, do daytime conversions, things like that. So using C# and Filey.net SDK, we had a very powerful mapping solution we could implement. What we do is we map whatever we can. And with that, I mean that we don't have any knowledge on cardinality, on required elements. We just process whatever we can and we leave it up to the validation component to decide whether or not it's valid. The reason for that is that we didn't want to have the same logic in two places. This one decides what's valid fire, this one just tries to map whatever it can. The mapping turned out to be highly reusable between these two hospitals. The reason for that is, of course, that they both standardized on these zips. But still, it took about a day to implement one zip. And then for the second hospital, it took less than a day. And most of the time went actually into writing the unit tests. The fire server is being called by the transformation component for terminology-related efforts, and in time there will be an external terminology server for things like SNOMED and LOINC. Right now we do not support that. Then the second step of the transformation process is the validation. It's a dedicated validation component. The reason for that is that validation is quite expensive. It takes time to do. And if you remember, as I said, if something takes longer, then we can spawn more instances of it. So the same applies to the validation component. If there's a lot to be validated, then the validation component will not be the bottleneck. It offloads the fire server. The fire server that we use can also do validation, but it needs to ingest the information that we're sending to it, so having a validation component makes sense. What it does is fool the validation against a profile, and the outcome is very simple. It either succeeds or it fails. And if it fails, it ends up on the aforementioned dead letter queue, and if it succeeds, it gets passed along to the next component. That's the loading component, and it's really simple. It just does a put to the fire server, and then the information is stored there. That's this route. So new information, either the initial load or an update on an existing patient, we transform it, we validate, and we load it. And then we have these two other routes, patient merge and deletion. The patient merge becomes relevant when you come to the conclusion that you have two patients in your EHR and they're the same. So you need to merge it. What happens is that they do the merge in the EHR, and then they give us a full batch of new patient-related resources. So we get the patient and all the related resources through the route that you just saw. However, the lab system and the medication system, it's more tricky to get the information from these systems once it has already been provided. So what we do is we have written a plugin in Filey Server, so we've extended the functionality of Filey Server, and we trigger a merge operation in which we provided the old patient ID and the new patient ID. And then two things will happen. First of all, we'll do a rewrite of all the references of the resources that I just mentioned for lab and medication to point from the old patient to the new patient. And then we remove the old patient together with all the other resources that we're getting anyhow with the update of the new patient. And when I say remove, I mean erase. So we support something called an erase operation in which we really delete the fire resource and all of the versions. We don't just flag it, but it gets completely removed from the fire server. That's the patient merge. That only leaves the deletion, and the deletion is done on a zip instance level. So you can delete a specific observation, you can delete a specific other type of resource. It's again an erase with full deletion. Another problem that we solved is that of tracking and updating. So as you've seen by now, there are quite a few components. There's a whole route that information flows through, and at many places things can go wrong. So what we did is we introduced something called a correlation ID, which gets added to data the moment it gets produced in the source system. So if the source system has an update, it generates a unique ID, that's the correlation ID, and then the correlation ID gets passed along all of these components. If there's anything to be logged related to the data, we log it combined with the correlation ID. So if anything goes wrong, we can look in the logs of the other components and based on the correlation ID, see which events came before. The second thing we do is we add a source system label, so we keep track of which source system provided this information. And the last thing is that we also keep track of a date timestamp on when the update occurred in the source system. And as you'll see in a moment, the last one is really important. So we've looked at the source systems. They have all sorts of data. They look at the fact whether or not a patient is active. If so, the information gets fed to the ETL pipeline. This switchboard transforms the information, validates the information, and then loads it into the FHIR server. Now, for the FHIR server, we have two different flavors. We have an inward-facing and an outward-facing FHIR server. The inward-facing FHIR server is the one who is not accessible from outside of the hospital, and it gets fed all of the information from the ETL process. The first purpose of the inward server is to, of course, offload the outward FHIR server, but it also has a number of plugins loaded in there. One plugin is the patient merge that I just discussed. The other plugin is a plugin that decides whether or not to update information. As I just said, we have this label, this date timestamp of when an update occurred. And it's really important because if you have two subsequent updates for the same resource, for the same patient, for example, and they both get fed to the ETL process, it could be that you have multiple consumers working in parallel. And that could, as a result, have the effect that the newer message hops over the older message, and the newer message gets processed before the older message. Then if the older message ends up at the FHIR server will look, oh, I already have a newer version of this patient resource, so I'll just discard the update. And since we're not using anything like patch, it's always a full update coming from the source system, we can just safely ignore this update. Sorry, I need to get a sip of water. So that's the inward-facing FHIR server, and it writes the information to a SQL server. And that SQL server is shared with the outward-facing FHIR server. Now, of course, the outward-facing FHIR server offloads the inward-facing FHIR server, but it also has authentication and authorization enabled, whereas it's disabled on the inward FHIR server. The inward one is in a secure environment, so there's no need for that. We don't need the performance overhead of security, but we do need it, of course, with the FHIR server that we're sharing to the outside world. And furthermore, we can put a load balancer in front of it so it can also scale horizontally. Now, we've reached the point where the information from the source systems has gone through the ETL pipeline and has ended up in the FHIR server. And now we get to the next step, which is actually sharing this information with another hospital. So we have the referral process, information being sent to the prostate cancer center, and then eventually when the patient is treated, we have the discharge flow. Now, this is actually the point where we are at right now. And the information will be less specific because we're still figuring out how to do stuff. And we also have now more of a reliance on some external parties, but I still want to give you some insight on where we are. So some of the challenges that we follow when it comes to sending is, first of all, how are you going to filter what information you're going to send? Then where are you going to send it to? To which hospital, to which department? And if you know where you're going to send it to, then how do you know if you can actually trust these organizations? How do you set up a trust layer? So basically the question is, what does the flow look like for sending out a referral? What we think, what it should look like is that, first of all, there's a trigger from the EHR, which gives you some context. It tells you something about the use case and it tells you something about the patient that it's about. And then you need something like a referral UI. And do keep in mind, they're changing their EHR, so it was not an option for them to extend the EHR. Therefore, we have a separate referral UI. This referral UI can be pre-populated based on context. So if it's for prostate cancer, then there are a number of SIPs that we can pre-select. we can pre-select it, but you also need to be able to deselect it, of course. You need the option to add additional information. Maybe you have a letter you want to send along, or a DICOM image that's not yet in your file server, so you need to be able to add that information as well. Then you need to select where you're going to send it to, and then, of course, send out the referral itself. You see here from the referral UI, it has a link to the file server, because that's, of course, where the data is, and there's this thing called a nuts node. And the nuts node is the thing that facilitates the trust layer and this notification. Nuts in itself supports a trust layer. I'm not going to go into the details. I think I'm giving you enough details already, and I also don't have the time. But the main takeaway here is that it supports the concept of a notified pool, and that's a very elegant solution. So what happens with a referral in our case is that you send out a referral, but you basically just send out a notification on the fact that you are planning to refer a patient. And that referral notification does not contain any sensitive information whatsoever. It ends up at the hospital that you're referring to, they get a notification, and then only when they decide to actually open up that notification, they reach out to the file server that has all of this information, retrieve it, and process it. So only when the hospital decides, okay, now I'm going to treat this patient, then information is being transferred between the two hospitals. It also has a registry of other nuts nodes, so basically of other hospitals that support this level of trust. And they also list the use cases that these hospitals support. So we have quite a few. We have e-overdracht, we have Baby Connect, we have the VIPP program. You can list all of those in there, and then you can see, okay, what parties could I in theory exchange information with? There's a really nice talk on this topic tomorrow. The same time slot as today. Jort Spee is doing most of the talking. He's from NUT, he knows all about it, so he'll do the explanation. And I participated in a Connectathon a while ago and wrote a simple file server plugin, and I'm going to explain some details on that. So if you want to know more about NUTs, then please tomorrow, same time slot. This is a mock-up of what a referral UI could look like. So here you select who you're going to send the information to. Here you can add some additional documents that are not yet in your file server. Here you have the zips. They are categorized based on how the categorization is done in the zips. So your patient would be here, for example, and then you can just select which zips you would like to send over. Now, once you send it over, there are new questions. How are you going to be informed on the receiving party that there is new information? How are you going to decide which information you're actually going to accept? And if you accepted information, where are you going to store it? So you need another referral UI on the receiving end. They receive this notification, and then the first thing that would make sense for them is to have an overview of both the incoming data and the data that you already have. And there needs to be some smart deduplication in there, because it could be that you already have some information on this patient. So we need to make explicit to you, well, this is new information, and maybe even this is new information related to this specific use case, to this context. Then you need to select what data to accept. And then once you accept it, the data needs to be tagged, indicating that it's coming from a different source, and then stored in the file server. This is what a merge pane could look like. So here on the left-hand side, you have the hospital that's doing the referral, and they show the information that they're sending over. Here you have the information that you already have. As you can see, there are two zips here that overlap. They exist in both systems. And then here's a zip which is new and relevant. So you just check it, and then you can decide to accept the information. That's a referral, and basically once the patient is treated and you're sending the information back, it's the same process. So you need to select the patient, you need to select which information you want to send back, where are you going to send it to, and then once it gets to the other hospital that did the initial referral, they can decide to adopt this information and store it. For now, these hospitals decide to store the information in their file server. So upon the discharge, that's where it stops. You could, of course, take it one step further and say, okay, we want to take this information and store it in our EHR, which means that you need to implement the opposite route in your ETL pipeline. That's a lot of work. And again, because they're going to stop with this EHR, they decided not to go that route. What did you learn? Or maybe I should say, what did we learn? Or what did we all learn? First of all, standardizing your data output helps. Just looking at the source systems, that they already did some kind of standardization based on these healthcare information models, that helped a great deal in the whole process of data transformation. A message-based solution is a really good fit for an ETL pipeline. It's really scalable, it's really flexible. It's really nice to have these single responsibilities, and we believe it's not just suitable for a use case like VIPP5 module 3, but basically any use case in which you just have information flowing around in the system and you need to do stuff with it. Expressing transformations in C#, it's very flexible. Of course it is, it's a programming language, but it also turns out that it's quite reusable. And even if we get to a first customer that doesn't have the same output from the source systems, we still believe that we now have some kind of templates in place that would still minimize or lower at least the implementation effort. The cloud is not a requirement, so everything I've told you now is based on an on-prem implementation, and of course you can do the same things in the cloud, but it's not necessarily easier. Because if you do it on the cloud, you need to understand how does it work on the cloud. And one of the things I'm mostly interested in is a year or 2 years from now, what do the financials look like? What is going to be the expensive solution and what's going to be the cheaper one? To give an example, a service bus is relatively cheap on Azure unless you have messages which are larger than 200 kilobytes. Then you get to the enterprise level service bus with the enterprise price tag. So things like that happen in the cloud, they don't happen on-prem. The last thing we learned, all of this is still relatively new. So we needed to figure out a whole bunch of things, and there are still more things to figure out, which is fun. And I hope you now have a few things less to figure out if you ever get to this point. If you want to reach out to me, of course, you can do that on Bova, or you can send me an email. There's a big feedback form here in case you want to take the effort, and if there are any questions, then please let me know.
Thank you for the nice presentation.
I haven't answered the questions yet, so I'll wait with the applause.
How do you handle the identification of patients? You refer a patient from A to B, and how does B know which patient does he get?
It's the Dutch social security number, the BSN. So that's basically the thing that indicates which patient you're talking about.
Okay, that's forbidden in Switzerland. That's our big problem.
It depends on the use case. You can't always exchange it. In this case, there's something called a legal ground to exchange the information, so you don't need to confer with the patient, and you can send over this type of sensitive data. But there are also use cases in which in which it's trickier to share this information. And for example, the notification task that I mentioned, it doesn't contain the BSN at all. It's really just when you start the retrieval process, then it becomes clear what patient it's actually about. So we try to minimize that as much as possible, but yeah, for now it's the only thing tying the two patients together.
Yeah, makes sense.
Yeah.
What things will make your validation fail? So errors obviously will make your resource be rejected, but if there's warnings or informational messages from the validation process, what happens then?
Yeah, so warnings we ignore for now. That's also because we get warnings on the fact that we're using the Dutch display values, and the validation engine checks on that as well. One of the things that we encounter are bindings to required bindings to SNOMED, for example. So that's something that's definitely going to fail. If we can't validate the SNOMED code in there, it's an invalid SNOMED code, and that's going to be rejected. And of course, things like cardinality and such. Yeah, the usual suspects, I would say. Yeah.
And going to that again, how are you dealing with semantics? I mean, if you need to map the source systems into a FHIR resource, and they're using some internal codes, are you planning to map also those codes to some standard code system that you have?
Yeah, that's actually where the C# comes in handy. So you can really sit with the client and understand what it looks like, and basically it's going to be a switch, or if you want to make it a bit more fancy, it's going to be a concept map, and then you load that concept map into your fire server, and then you ask it to resolve it for you. But you do run into situations like this where you need some breakout logic, and that's why having a fully fledged programming language is very convenient, as opposed to something that's perhaps more structured but will get you into problems somewhere along the line. Does that answer your question?
Yeah, sure. Thank you.
Hi, thanks for the presentation. So the fact that source systems are going through the ETL pipeline, is that a midterm solution and the end goal of them going directly to file server or not?
That really depends on the new systems. Your question is, how is it going to be in the future, right? I don't know if the EHRs that they chose are actually very willing to support Fire. I know that one of them is not. I don't know about the other one. So yes, it would make sense if the EHR would have a Fire interface, and it would make sense if your document store has this MHD profile that you can have Fire interaction with it. But for now, it seems like most vendors are not chomping at the bit to put a Fire API on top of their systems. So I guess the answer is no.
Okay, thanks, sadly. And one more, if I may. When the zips get pulled over as part of the notified pull, does that mean a duplication of data at the end hospital or not necessarily?
Well, that's why you have the merge, of course. So there's no filtering being done upon retrieval. That in theory that would be possible, but then you need to think how you're going to correlate the two. For a patient, it would be the social security number, but how are you going to correlate observations if you don't have the same IDs? So yeah, now you pull over the information, and then it's really up to the system that's showing them to do the deduplication, and of course the user to say, well, I don't need this information, or I already have this information. Does that answer your question, or did I misunderstand?
I think it does. So it's in the domain of the second hospital to decide whether they're going to actually store the data and duplicate it effectively or not.
Yeah, correct.
Okay, thanks.
Yeah.
So the system, the ETL process, more or less copies data into the Fire server, and then you accept updates on the Fire server.
Mm-hmm.
So the ETL is one way. Did you have any issues with data not being updated on the source systems? So source systems still working with old data?
Did we have any issues with that? Well, not yet. It's bound to happen. Can you be a bit more specific about, I mean, you just mean that we missed an update in the source system. Is that what you're saying?
I was just wondering that you introduce a new system which accepts updates, and then the old system, I mean, you're changing the way in that, the environment in a way that you have two systems which may have data about the same patient, where one is updated and the other one is not. So then the source systems must be working with old data, am I right?
The source systems never work with all data. So the source systems always, oh, you mean if information is coming back to the Fire server? Sorry, now I understand your question. Yeah, and that's a good question. So yes, normally you would feed it back into your EHR, into your source system, so the information is up to date. They're not doing that because of the fact that they're changing the EHR. So now some process needs to be filled out within the organization that if for the specific use case you want to have a complete patient overview, there will be a shared view. There will be part of the information coming from your source system, and part of the information will be coming from the referral. And then your question probably is, if you have discrepancy, how are you going to make sure that your source system gets aligned with the incoming data?
Yeah.
Yeah, we don't know yet.
Okay, thank you.
Good question. Yeah.
Do you expect to have more use cases like this one in the future? And do you think the solution, as it is structured now, is generic enough to support those use cases?
And do you mean within the same hospital, or?
No, like different Dutch subsidies, grants.
Yeah, because it's not really tied to a specific solution. I mean, the only thing that really ties it to the VIPP program is the way that we structure the data. I think the solution that we have now is basically implementation agnostic, and the only thing that makes it specific is A, your transformation, and B, what profiles you load into your Fire server. So I think if you want to assess how reusable it is for a different use case, it really depends on how much the zips are alike, but the whole infrastructure is something that can be reused. And now we have a message indicating there's new source data. We can also have a message saying, well, there's new source data for this specific Dutch program. So I want you to transform this to an overdracht type of flavor, or this is something else. Yep.
This would be a bit of a nasty problem to have, but what happens if your message queue itself crashes?
Well, the good thing is that for now, the EHR is always a single source of truth. So if it crashes, we need to assess when it crashed and then get all of the updates that happened since that time. And that is doable. Yeah, it's basically like the initial load. And if it really turns sour, you can always delete all of the data and do an initial load for all of the patients. And then your two systems would be in sync again. But having a more elegant solution would be advisable. Yeah. And that's one of the reasons that we also chose this registry of active patients, because we just didn't want to load all of the information and then come to the conclusion that we need to change something, get rid of everything and reload it again. Now it's just something that grows over time, and hopefully by the time it gets to a lot of data, we have ironed out most of the issues. Okay.
No more questions? Okay. I think we also don't have any questions from the Hoeva app, so if you have additional questions later on, please ask them via the app. Frank, thank you for the nice presentation.
Thank you.
And please give feedback via the link that is provided on the screen.